Hi guys, we're carrying on with aircraft flight mechanics. We're now just going to pick up where we left off. So we went through a worked example last time, or I went through a worked example or told you to look at it basically. Then we went through the Boeing 747 in power approach condition, taking the non-dimensional stability derivatives and turning them into the dimensional ones. And we then used the longitudinal A matrix, and we also had to use the B matrix to excite the system. But we're going to show that actually all of the stability characteristics just come from that A matrix. We then found these plots, and we said that there's two sort of characteristic motions occurring here. We see some long-term motion, and we see some short-term motion. The short-term really only seems to be affecting the heave, which is the angle of attack, and to a little bit the pitch attitude, but mainly the pitch rate. And then there is this longer-term oscillation that is really affecting forward speed and pitch attitude, but conversely not affecting either heave velocity or pitch rate very much. So we did that, and then we looked at the same in the lateral directional. We saw there's some sort of oscillatory motion occurring here and some non-oscillatory motion occurring here. Probably should have said back here that we've got two oscillatory sort of things occurring in the longitudinal. And then we said for lateral directional, we got something oscillatory and something non-oscillatory occurring. So we're going to look at the A matrix. We're going to have a look at how we can identify and separate out these two characteristic modes of motion for our aircraft. So we might need to do just a little bit of revision on sort of simple harmonic motion, and we'll think of the simplest system we can analyze. So hopefully this is revision, but as I've sort of remembered from being an undergraduate myself, you often just forget a lot of this stuff as we go through. So we'll have a 1 degree of freedom mass spring damper system. So it's got some sort of linear spring of stiffness K, some sort of dashpot damper of a damping C, and there is one single displacement ordinate that we've got here, which is X. So our forcing for this system is a force in the X direction as a function of time. So again, this is the simplest system that we can get. You would have gone through this in previous courses and sort of derived the equation of motion for this system. So we have an acceleration term, which is the mass. This just comes from Newton's second law. We've got a term that's proportional to the velocity, which is the damping. And then we've got the stiffness, which is proportional to the displacement. This at any time has to be equal to, well, this is all from Newton's, this is from the sum of forces equaling 0. The external forcing has to be equal to this at any time. So for free vibration, there's no forcing on the system. Then we have just set the right hand side of this equaling 0. So we can represent the system, and hopefully this is where I'm saying it's revision for you guys. Then this should look familiar if I was to write it in the form. Okay, so I've now got effectively a quadratic equation here, and I've got some things that are going to help me understand how this system works. So omega n, the natural frequency, and then zeta, I'll make it very clear that's a zeta, is the damping ratio. So the natural frequency determines the speed at which any oscillations occur in the system, and the damping ratio is a measure of how much energy is taken out of the system with every cycle, effectively. So hopefully you would have gone through a solution of this in the past, and you would have said, okay, well, we're going to assume our solution is of the form So we'll assume that x is equal to a, just some constant multiplied by the exponential e lambda t. Okay, so we can then go through the calculus. X dot is equal to lambda ae lambda t. X double dot is equal to lambda squared ae lambda t. So we can then take these, substitute them back into our original equation, and we end up with, so I want to substitute these into here. So I get x squared a lambda t plus, and then I'm substituting this into 2 zeta omega n multiplied by x, sorry, x single dots. And then this last term, I've got omega n squared, so I've just got that here. I don't need to put it down again. No, I do, because I'm missing an x up here. I'm missing an x here, that's why. So I do need to put that in. So I then have here ae to the lambda t. Okay, we can cancel all of these a to the lambda t's. This is then a quadratic, or the characteristic equation of this system. So this is the characteristic equation of our mass spring damper system. You might wonder why I'm going through this with you, because we're going to use this exact same approach for our aircraft. And through speaking to you guys this week, I found that not all of you are entirely familiar with this formulation, maybe because you've forgotten that you've gone through it. So we're just going to have a quick revision of where we kind of sort of came up with all of these things. So the roots of this equation give us or will be able to tell us about the stability of the equation, and we'll show how. So using the quadratic formula, the roots of this equation are omega n minus zeta plus or minus the square root of minus zeta squared minus 1. Skipped a couple of steps there. And then we can show the general solution of this by just putting these back into the equation again. Remembering we have two roots, okay, because we've got the plus and minus sign here. So the general solution is going to be a function of those two roots and then these two amplitudes a and t. So I could then rewrite this whole expression as substituting the general expression for the roots lambda into this expression now. this shouldn't be a plus or minus, that should just be a plus because I'm putting these two in as the two separate roots. So that one's a plus, this one becomes a minus. So this bunch of stuff, or the two things inside the square root, is called the radicand because it's inside a radical symbol. But effectively, the size of the damping ratio zeta is going to tell us the different types of damped motion, whether it's going to be over damped, critically damped, or under damped. So we can see that if zeta is greater than 1, then we'll have two distinct real numbers coming out of this expression. If zeta is exactly equal to 1, then these two are going to be equal, so we'll have two real equal roots. And then if zeta is greater than 1, then we're going to have a complex conjugate pair of roots coming out of here. Because if zeta is less than 1, then we have a square root of a negative number. So this is where we have a complex root here. So we've got three different types of roots we can get out of the characteristic equation, all of which confer to, these are the roots here, so we can have real, distinct, and negative. We can have real, negative, and equal, so we've got two roots that are exactly the same, or we can have a complex conjugate, giving us two pairs with a real part plus and minus the imaginary component. And then these give us three different types of motion. We can have overdamped motion, which is where we've got 0, say we've got a initial disturbance. This is just some state variable as a function of time. Then after this initial disturbance, returns to 0 with no oscillation in some sort of period of time t. If we have critically damped, then we have a return to 0 in the shortest possible time. And then if we have a complex pair, then we have a motion return to t goes over it, so we have an oscillatory response. Okay, so these are the three types of damped motion that can occur for the mass spring damper system. But there's another type we can have for the aircraft, which is where we have excitation as well. But we're going to look at these for the moment. Now this one is what we'll see most of the time on aircraft. We'll tend to see this underdamped motion on aircraft. We'll very infrequently see critically damped motion on aircraft. We're not lucky enough to see that. So we can rewrite the expression for the general solution for this. We can say xt is equal to we'll say, again, this isn't from memory, I'm having to look these up as I'm doing this. E to the I 1 minus theta squared omega nt plus a2 exponential minus I 1 minus theta squared omega nt. So this is only for the case where we've got underdamped motion multiplied by e to the minus theta omega nt, which means we can then introduce something called the damped natural frequency, which is a relationship between the natural frequency and then the damping ratio theta. So we say omega d is equal to omega n multiplied by 1 minus theta squared. So it's actually the frequency with which a damped system will oscillate. So the natural frequency is how it would oscillate, and the period of those oscillations where there's no damping present in the system. But we introduce this part here called damped natural frequency. Okay, so if we have positive damping in the system, generally means the system moves slower. So the damped natural frequency will be lower than omega n. And we can see that here because 1 minus theta squared, when theta is less than 1, this becomes a number smaller than omega n. So for this case, we can then say xt is equal to a3 cosine omega dt plus a4 sine omega dt multiplied by e to the minus theta omega nt. A3 is equal to a1 plus a2, and a4 is equal to a1 minus a2. So we can put it in this expression for the case where we've got this underdamped motion, and we'll see this often on particular aircraft. So gone through all this. Hopefully this is a revision of what you guys have done in sort of basic system analysis and sort of a basic of how systems work. The reason we're going through this is because we're gonna use these routes to determine the stability of different modes of aircraft motion. So we produced the characteristic equation for this system here. This was for the simple mass spring damper. Now we're going to produce characteristic equations for different modes of aircraft motion. So we're going to talk about some different types of the routes that we can get out of characteristic equations, because we spoke down here, we said, well, the damping can give us these forms of motion, and we're going to talk about how they relate to the routes that we get out of our different characteristic equations. So let's make a new slide for this. You guys will see that we got that characteristic equation in the form lambda squared plus 2 theta omega n lambda plus omega n squared is equal to 0. So we got it in this format. If we'd taken the equation of motion with 0 initial conditions and then did a Laplace transform of it, we would have arrived at the characteristic equation in terms of the Laplace operator and not lambda. So we would have ended up with s squared plus 2 theta omega n s plus omega n squared is equal to 0. And we should know from sort of system stability and analysis that the poles of the Laplace form of this give rise to the system stability. So it follows that the eigenvalues, which are the roots of the characteristic equation, will give us the stability of the system. And again, we've shown that the eigenvalues or the root, so the eigenvalues of this system are given by the roots of the characteristic equation. So we ended up showing that lambda is equal to omega n minus theta plus or minus theta squared minus 1. So for a mechanical system, like the mass spring damper, damping can only be positive. And so hence the term here, zeta omega n, can always be a positive thing. And this is sort of a consequence of the fact that physical damping is just a removal of kinetic energy from a system. So it's always going to cause oscillations to decrease in amplitude. So if we've got a mechanical system, we can have an oscillation that decreases with amplitude. So we've then got, let's draw this a little bit better. So this exponential decay is determined by the damping of this system. By the damping ratio. So it means that the roots of the characteristic equation of something like a mass spring damper, they'll always be sort of real and negative. So they can be real or complex, but they'll always have a negative real part. For an aircraft though, there can be an interplay of kinetic energy and aerodynamic excitation that causes us to be adding energy to a particular mode. And if rather than we're taking kinetic energy out of the system with a mode of motion, we can be adding it, this means we've got negative damping in a system, which means that oscillations can increase with respect to time. So for an aircraft, by contrast to a physical system, we can have oscillations that increase in time. And this means that we've then got negative damping. And obviously we want to know when this can occur on an aircraft, so we'll talk about this in terms of the roots of any characteristic equation that we might end up discovering for different aircraft motion. So types of roots we can get a real and negative root. Now this is similar to, it's exactly the same as the mass spring damper system. If we've got a real negative root, it means we have a type of motion that has exponential decay or convergence to a final value. It gives a static stability with no dynamic phenomena. So it says statically stable, non-oscillatory. And again, if I was to draw this, this is some variable x as a function of time. Then after an initial displacement, if we have a real negative root, then we see exponential decay with no oscillation. We've got a real and positive root. Then this is statically unstable. And this is still non-oscillatory. So what this would look like is, again, same system. It can't be the same system because it's exhibiting different phenomena. But let's say this is a similar system. This means that after some initial displacements, we would see exponential divergence, or again, this idea of static instability. And both these modes are non-oscillatory. We can then have complex, two types of complex. We can have a complex root with a positive real part, or a complex root with a negative real part. So we'll say complex. So this means that we've got a real part, 2 lambda, and an imaginary part, 2 lambda. Okay, so that's funky RE, funky IR. Sometimes I'll write them like that. Sometimes for convenience it's easy to write lambda with the subscript R, lambda with the subscript I, just for looking at these 2 different parts here. More often than not, I'll use this notation. Say we have a complex, but we have the real part of lambda is negative, so it's less than 0. Then we have this tendency to return to 0, so it's sort of static stability, but we have oscillatory motion because we've got a non-zero imaginary part. So this is dynamically stable, so it's oscillatory motion with a decreasing amplitude. Again, similar system. Oscillatory motion with a decreasing amplitude after an initial disturbance. There we go. We see this exponential decay in terms of this response. So we've got dynamic stability. And then the other one, we can have complex with a real part that's greater than 0, or a positive real part. Again, because we've got complex, it's therefore got oscillatory motion with increasing amplitude. So this is therefore statically unstable. Sorry, dynamically unstable. So time, you'd see oscillations increasing with time. This is exponential increase in the size of any oscillations here. So if we can work out the characteristic equation for aircraft, sort of types of aircraft motion, then we can use the roots of that equation to look at its stability. So we need to take what we did for this 1 degree of freedom system and extend it to a multi-degree of freedom system. So because at the moment we're not looking at stability involving the any form of control, we're going to just use the A matrix or the system matrix. So again, we're looking at this idea of free vibration, how the aircraft wants to move. So this is then just x dot is equal to A x. Okay, so this A matrix is either going to be the longitudinal or the lateral directional system matrix that we found before. So what we've got above here, so rather than having a single equation of motion that we have for the mass spring damper system, we've got a system of n. We've got a system of n equations. Okay, where n is just the number of states and therefore the degrees of freedom in our systems. So we can just put the exact same general form into the above, and we can say that for x, from x as being 1 all the way up to n, xi is equal to x naught I multiplied by e to the lambda t. I is from 1 to all the way up to n. So for our longitudinal equations of motion, n is 4, lateral directional, n is 5. So we can then write this in vector format. Hey, Poppy. Our x vector is equal to x naught multiplied by e to the lambda t. So again, just as we did before, we can differentiate this and put it into our generalized expression at the top. And we can then write this as some calculus and some substitution, and we will end up with lambda multiplied by x naught e to the lambda t is equal to the A matrix multiplied by lambda naught e to the lambda t. So we've got an eigenvalue problem. It's a matrix vector problem effectively, so we can write this as more, it's going to help us solve it if we write this as, and we can turn this into an eigenvalue problem. We can say lambda multiplied by the identity matrix minus the A matrix multiplied by x naught is equal to 0. So this is our problem to solve, and there's a trivial solution which is just x naught is equal to 0. The more useful solution is found from the determinant of this left hand side. So the useful solution is going to be found from lambda I minus A is equal to 0. And what we have here, what we're going to get out of here, will give us the characteristic equation of a multi-degree of freedom system. So if we were doing this by hand, we'd have to work out the determinant of a 4x4. So we do this in steps. We do lambda multiplied by I is going to be lambda, 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 lambda. We then have our A matrix is same A matrix that we've used for the rest of this. So we've got xu, xw, 0, minus g, cosine theta naught, and so on. This will be the rest of that matrix. I can remember the first line, but not the rest. We then go through and you'd have to do the determinant of a 4x4, and what we get out of that would be a quartic expression. So we then end up with lambda 4 plus A multiplied by lambda 3 plus B lambda squared plus C multiplied by lambda plus D is equal to 0. So we've got this dirty great expression that explains what we need to know about our aircraft. So we can do this. We can get this equation. It's pretty easy to do. Let me just go back to the accompanying notes, or to my sort of version of the accompanying notes. So what we're after is the eigenvalues, which is what we're actually going to end up with, but there's ways you can use NumPy to get the characteristic polynomial of any sort of matrix. So I've got my A matrix here. Characteristic equation is simply found by doing np.poly of your A matrix. And then this gives me the characteristic polynomial here that I can get out. So I've got lambda squared plus 1.05933 sorry, it's not lambda squared, that's lambda 4, that should be. That's lambda cubed plus 0.78020 lambda squared plus 0.02312 lambda plus 0.015088 is equal to 0. So this characteristic equation is the coupled, sorry, I don't want to say coupled, it's the response of the aircraft in longitudinal motion that captures both that short and long-term behavior that we saw exhibited. Now, we can factorize this into two quadratics, and each of those quadratics would give us the characteristic equation for those two modes of motion. We can just get the roots of this though, because I'm no longer teaching this where you have to sit down in an examination and do some form of factorization, which you can do using some analytical expressions. You might as well just get the eigenvalues straight out for this whole equation. So to find the roots of this equation, you could do roots on the polynomial here, and I've just shown that these two ways are equivalent. You can print out the eigenvalues of this matrix just by using a bit of linear algebra using NumPy, print out these eigenvalues, or you can do the roots of the characteristic equation. That's exactly the same thing. So I'm just going to write these eigenvalues down. So lambda 1, I've got two sets of complex conjugates. So lambda 1 is equal to minus 0.52829 plus or minus 0.69158, and then lambda 2 is equal to minus 0.00137 plus or minus 0.14114i. So those sorts of motion that we saw, remember we saw something that was quite short-lived, very heavily damped, and something that was long-lived and lightly damped. They correspond to these two sorts of motion. And we're going to work out how we can get them out of there, how we can determine which is which, and then we'll give them some names and we'll talk about them a bit more. So these are the eigenvalues for longitudinal motion using the data that we took for the Boeing 747, and then we can then think about how these refer to the actual how they refer to the actual aircraft response. I'm just mumbling now, sorry. So let's see if we can put one of these back into sort of quadratic form, and then we'll compare it with the standard form, and we'll see if we can determine a means of converting between those two. So what we've got here, we've got lambda is equal to the real part of lambda plus or minus the imaginary part of lambda multiplied by the imaginary operator. So if I wanted to recreate those two quadratic equations, I could then, if these are my roots of that equation, I could then recreate my quadratic equation by saying lambda minus lambda 1 multiplied by lambda plus lambda 1 is equal to 0. So that's then my quadratic equation. I'll get this back. Now when we've got a complex conjugate, we don't change the sign of the real part, we change the sign of the imaginary part. So I would have here, I'm going to replace these, I'm actually going to change, just so I don't have to keep writing out these funny e's and i's, I'm just going to replace these with r and I for the moment, just to help me a little bit with this next part. So I've got lambda minus r plus I multiplied by I multiplied by lambda minus r minus II. So let's expand these out. I've got lambda squared. So let's look at this. I'm going to have some lambda terms. I'm going to have r multiplied by lambda, and then I'm going to have r multiplied by this lambda, and I'm going to have I multiplied by lambda, I multiplied by lambda, but these two are going to cancel actually. So let's multiply these out. So I'm going to have minus r lambda plus, sorry, that's going to be minus I multiplied by lambda minus r lambda plus I lambda, and then I'm going to get these two things squared together. So I'm going to get plus r squared plus I squared here. There we go. You might want to just confirm when you multiply these two out, the i's cancel, but I know from doing this that those do. So these cancel. So we've got lambda squared minus 2r lambda plus r squared plus I squared is equal to 0. So this is a characteristic equation of one of the, I could take either the real and the imaginary part of either of those roots, and I could put them back into this form, which gives me the characteristic equation. So remember, the generalized form of our characteristic equation is lambda squared plus 2 omega n lambda, plus 2 zeta omega n lambda plus omega n squared is equal to 0. So we've now just worked out that actually we can get the natural frequency, because the natural frequency is going to come straight from these two things here. So we have just shown omega n is equal to the square root of the real part of our root squared plus the imaginary part of our root squared, or the absolute value of the root. And then we can similarly see the damping ratio is going to be equal to minus the real parts divided by the natural frequency. So we can get the natural frequency and the damping ratio for our aircraft based upon these roots up here. So these roots, we can work out which is which. I know from looking at these, I can see that, well, in fact, let's take a step back a second. We can see here that the actual damping ratio is really going to be a function of the roots, of the real part of the roots, and the natural frequency, and then the natural frequency is going to be the vector sum of both parts here. So this means we can immediately get the natural frequency of these two modes of motion. I'll tell you what you can also do, and you can go through it if you wish to, remembering that we said omega d is equal to omega n multiplied by 1 minus zeta squared, then what we can actually do here is we can see, and you should be able to see, that omega d is simply equal to the imaginary part of the root. So the damped natural frequency is the one that we actually see exhibited in motion. So let's go back up to these. We can immediately see from all of these that the damped natural frequency is going to be 0.69158 radians per second. Omega d is equal to 0.14114 radians per second. So let's think about what these two things actually mean. Now, the damped natural frequency is the actual time the system takes to respond. The natural frequency would be the sort of the frequency that would occur if there was no damping present. So if we want to know the period of any oscillations, then this is the one that we need to use. So let's use this. So the period of any oscillation is going to be 2 pi divided by omega d, which is going to be equal to 2 pi divided by the imaginary part of these roots. So the period of this oscillation is, let me find my calculator. That's here, it's hiding. Okay, the period of this one is 9.09 seconds, and then the period of this one (44.5 seconds). Now, we spoke about these modes of motion before. I spoke about them a little bit briefly, but I'm going to go into more detail in next lecture. This one here is what's called the Phugoid mode. This one here is called the short period. This is actually a very long period for a short period to have. I had to go through and double check that I got the same answer as someone else, because short period is normally only a couple of seconds, but the 747 is a big aircraft. If we go back to looking at the actual plots that we drew, let's just move these off screen. And if we look at these plots, let's have a look at the forward speed. So let's kind of zoom in here at all. I'm not sure if you guys can see this, but I'm looking at points on this plot. So I'm picking this one peak is at about 56 seconds. Second peak is about 99 seconds. So yeah, that's about 45 seconds in this period of motion here. If we zoom in on here, it's going to be very difficult to see this period of motion because we've got both this is trying to look at this sort of shorter oscillation, but let's see if we can, I can look at maybe a half period here. So from 1.4 seconds to 6 seconds. So that's maybe not even right, maybe like there, 1.4 to, yeah, maybe to 6. So that's about 4.5 seconds is the half period. So 4.5 times 2 gives us 9 seconds. So we've got the two parts of this motion out here, but we've managed to separate them out. Again, these are then the damped natural frequencies that we've just determined. Let's talk a little bit more about these two here. So we've got the damped natural frequencies. I'm going to leave it to you guys to get the damping ratio of these modes. If you want to post those on Slack, talk about it, then I want you to get those too. There's one more thing I want to talk about, which is what else we can do with the system here. So we can see for both these modes, importantly, they've both got negative real parts, and we can see from these sort of time histories that they both of these modes of motion had exponential decay, so they're both stable. Now, if we have a stable mode, let's just have a think about the two sort of modes of motion we can have. If we have a stable mode versus an unstable mode, then we want to be able to find a means to quantify, other than the damping ratio, in sort of pilot field terms. We want to talk about how we can quantify the exponential decay or the exponential increase. Now, this curve here is the absolute, is sort of the bracketing curve that would make our decay get either being decaying or increasing. So the amplitude of this oscillation, if it's going to be x is equal to x naught e, and then we just hit the real part of the mode. Okay, because if we don't have the oscillatory part and if we don't have the imaginary part, we then just have exponential decay. So the size of the decay of any of these oscillatory modes is just given by the real part here. So we can quantify the decay or the increase by either the time to half amplitude or the time to double amplitude. So we can just do that as a sort of solution of this equation. So we can show that, let's do the time to half amplitude. So we would want to end up at x naught on 2 is equal to x naught multiplied by e. So the real part of the roots multiplied by the time to half amplitude. So this is the bit that we want to get out. So we can divide both sides, but it doesn't really matter what the actual starting value is. So we can end up with natural logarithm of 0.5 is equal to the real part multiplied by the time to the half. So we end up with time to half is equal to minus 0.69 divided by the real part of our eigenvalue here. Very similarly, if we have an unstable mode, we've got this increase, we end up with the natural logarithm of 2, we just end up with t2 is equal to 0.69 divided by the real part of our eigenvalue, which is not negative in this case. So we've got these two modes these two means that we can talk about our modes of motion. So we can talk about them here. Let's say they're both going to have a time to half amplitude because they are both stable modes. So the time to half amplitude for the short period mode is going to be 0.69 divided by 0.52829. .306. So that's pretty quick. That's reduced to half the oscillation by the time it has gone to almost 1/4 of the way through, less than a quarter actually. So it's after 1.3 seconds, the oscillation's got half the amplitude it had previously, and the period of the oscillation is 9 seconds. So this is a very heavily damped system. Time to half amplitude for the Phugoid mode here. Again, we're going to talk more about these modes and how we can recognize them in the next lecture. This one is going to be 0.69 divided by 0.00137. 503 seconds. Whoa. Actually 504 seconds. So a long time. It's a very, very low damping in the Phugoid mode for this aircraft, and it's to be expected because it's a big aircraft. One thing I haven't got on here is I haven't given you guys the damping ratio or the undamped natural frequency omega n. Again, omega n is just the square roots of the real part and the imaginary part. So we can do it for this one here. I'm just going to be 0.87027 radians per second, and as we expected, this number is bigger than this one, because once we add damping to the system becomes slower. It's that term that gives us some removal of energy from the system, including removal of any speed with which it's vibrating. So we were able to take a look at producing some aircraft data. We took the non-dimensional stability derivatives for the 747, put them into state space form, and then excited the system and got some information out. And we were able to say, well, there's clearly two characteristic things occurring here. And when we spoke about them in terms of the sort of, one was short term, one was long term, and then actually all of them are just given by the eigenvalues of that matrix. And then by knowing a little bit about which one's which, we can talk about how we can get some characteristics out of them. So we then used the things that we developed in this lecture to talk about the natural frequency of each of these, both the damped and the undamped. So we've got damped natural frequency and undamped natural frequency. The damped natural frequency is the one that you'll actually see it oscillating at. So if you take the peaks and then divide them, take the peaks and then divide 2 pi by them, you'll end up with the natural frequency that you get from this one here. Okay. Conversely, omega n, this is the frequency the system would want to oscillate at if there weren't any damping that's removing or adding energy to the system here. So we've got this formulation that we can talk about different aircraft modes of motion, and I spoke about this idea of the short period mode and the Phugoid mode. So we've sort of gone as far as we can without talking about them more. We're going to talk about those and the other lateral directional modes of motion next lecture. So we've got short period, Phugoid mode, and we'll talk about those, and then we're going to talk about the lateral directional modes of motion. We've got one oscillatory mode, which is the Dutch roll mode, and then we've got two non-oscillatory modes, which is spiral and roll mode. And there's another mode that we don't really need to talk about, but we'll mention, which is just the fact the aircraft can yaw, because we're going to end up with another number in our equations of motion, or the solution of the eigenvalues of the system. We'll talk about that more when we get into next lecture. So that's as far as I want to take you this lecture. I want you to go through this example, see where these numbers come from, because you're going to need to be able to do this and get some information about these modes, and then following with the theory we're going to go through next lecture about what these modes actually physically mean, you need to be able to talk about them for the different aircraft that you've chosen to look at for Module 4 and consequently for Module 5. Hope that was interesting, guys. I love this stuff. I could talk about it for a very long time, but an hour is probably about as long as you guys can deal with in a lecture for now. You're probably going to get 2 more lectures this week. I hope you're finding it super enthralling, and I look forward to seeing you all in the review and hopefully in games night later this week.